They warp space, bend time, and swallow everything that comes too close. Across the cosmos, the most extreme black holes challenge everything we know about physics. Tonight, we'll journey into their depths and explore what makes them so powerful. If you enjoy the mystery, please like, subscribe, and share, and tell us in the comments, if you could safely visit a black hole, would you dare to go beyond the event horizon? Thank you for watching. Now, let's begin. The universe extends in every direction, a field of faint radiation, and countless galaxies woven into a structure of filaments and voids. Within this grand framework, gravity governs all motion. Stars form, age, and die under its quiet pull, while matter gathers into clouds, clusters, and spirals. Light crosses immense distances, revealing that even emptiness carries the faint memory of past events. At this scale, individual systems seem like grains within a boundless ocean. Galaxies cluster together, connected by invisible threads of dark matter. The larger structures grow slowly, drawn by gravity, and balanced by cosmic expansion. Inside them, energy radiates from stars, and yet there exist places where energy vanishes when no light can return. These are the black holes regions where matter collapses beyond all resistance. Seen from afar, they are invisible, yet their influence extends across thousands of light years. The universe holds them in diverse forms and scales, from small remnants of stars to titanic cores within the largest galaxies. To understand the most extreme among them, one must first picture the environment that allows such entities to form. In the early universe, energy dominated matter. Radiation filled space, carrying patterns that still appear in the cosmic background. As time passed, matter cooled, and the first galaxies began to assemble from hydrogen and helium. Gravity drew gas into dense halos, and within those halos stars ignited. Each galaxy became a laboratory of evolution, where cycles of creation and destruction unfolded. Amid these luminous events, some regions became dark. When massive stars collapsed, or when dense clusters coalesced, gravity reached limits where nothing could resist it. From those conditions emerged the first black holes, the silent anchors of galactic growth. Galaxies now number in the trillions, each containing hundreds of billions of stars. They take many forms: spirals with delicate arms, smooth ellipticals, irregular shapes shaped by past collisions. Yet at their centers, astronomers observe signs of compact and heavy objects. Stars near those centers move at remarkable speeds, following tight orbits that reveal an unseen mass. Radiation from surrounding gas shines across the electromagnetic spectrum, tracing the motion of matter as it falls inward. Through these signatures, the presence of central black holes becomes clear. Their gravity is immense, but it acts in silence. Only through its effect on nearby stars and gas can it be inferred. Observations from telescopes on Earth and in orbit show that the brightness of galaxies often correlates with the mass of their hidden cores. A small galaxy may hold a modest black hole, while a giant elliptical may harbour one with billions of times the mass of the Sun. This relationship suggests a shared history, an exchange between galaxies and their dark centres that unfolds over cosmic time. Some galaxies appear quiet, their central black holes inactive, drawing in little matter. Others blaze with extraordinary energy, outshining all the stars around them. Such galaxies are known as active, and their light originates not from the black holes themselves, but from the regions surrounding them where gas heats as it spirals inward. Even at great distances, these sources reveal their nature through radiation and motion. The Milky Way seen from within offers a familiar example. At its core lies a black hole about 4 million times the mass of the Sun, called Sagittarius A. It remains mostly calm, fed by sparse clouds drifting near its gravitational reach. Around it, stars complete orbits that confirm its presence beyond doubt. Similar central black holes are found in nearby galaxies such as Andromeda and Messier 87. The latter, larger by several orders of magnitude, has been directly imaged through its glowing surroundings. These discoveries form part of a broader pattern. Almost every galaxy appears to possess a central mass too dense to be anything but a black hole. They sit at the meeting point of cosmic structure and local dynamics, linking the motions of stars to the expansion of the universe itself. On even larger scales, black holes shape the behavior of galaxy clusters. When many galaxies gather under a shared gravitational field, their individual cores release energy that influences the surrounding gas. This energy, often carried by jets and radiation, prevents the gas from cooling too quickly, regulating the rate of new star formation. The result is a balance between collapse and heating, between accumulation and dispersal. In this way, the most extreme black holes exert control far beyond their size, affecting regions that span millions of light years. Their power does not come from motion or explosion, but from steady gravitational influence, magnified through the flow of energy in their environment. Across the universe, black holes reveal themselves indirectly. They cannot be seen directly because their escape velocity exceeds the speed of light, but their surroundings provide ample evidence. The motion of gas, the shifting of spectral lines, and the flickering of radiation all point to their presence. Modern instruments detect gravitational waves disturbances in spacetime caused by massive objects moving rapidly. These signals offer a new way to observe black holes independent of light. When two such objects merge, they emit a brief but measurable vibration that travels across the cosmos. Such events confirm what theory long predicted: black holes are not only real, but active participants in the universe's ongoing evolution. The cosmic landscape then is one of quiet extremes. Vast voids stretch between galaxies, yet within each system immense forces operate. Energy radiates freely in some regions, while in others it disappears entirely. Matter flows inward towards centers of gravity that never release it. From the perspective of a single human lifetime, these processes seem frozen, but over billions of years galaxies drift, collide, and transform. Their dark centers remain growing slowly as they absorb mass from their surroundings. The interplay of creation and collapse continues, guided by the same physics that shaped the first stars. To explore the most extreme black holes is to trace the universe's own balance between light and gravity. From the widest cosmic structures to the smallest observable orbits, the same laws apply. Gravity shapes the path of every particle, curving space itself, while energy radiates outward to reveal what would otherwise remain hidden. In this grand equilibrium, black holes stand as the purest expression of collapse, yet their role is constructive as much as destructive. They form the central points around which galaxies organize and evolve. Through them, the structure of the universe acquires both stability and depth. The next step inward is to follow how these vast cosmic systems give rise to their dark hearts, and how gravity turns from a gentle attraction into an inescapable descent. Within each galaxy, countless stars and clouds move under the combined pull of gravity. The pattern of this motion reveals a hidden geometry, one dominated by a massive center. Spiral galaxies with their bright arms and dusty lanes rotate around a gravitational hub that cannot be fully explained by the mass of visible stars alone. At the heart of these systems lies a region so dense that its gravity binds entire stellar populations. The presence of such centers was once an assumption, then a hypothesis, and now a measurable fact. Astronomers detect their signatures through the motion of stars orbiting nearby, and the behavior of gas heated to extreme temperatures as it falls inward. These regions do not emit light of their own, yet their surroundings shine with energy released by compression and friction. Each galaxy's central structure is distinct, yet all appear to share a common trait, the influence of an unseen compact mass. The Milky Way offers one of the most carefully studied examples. Near its centre, stars trace elliptical paths around a dark point no larger than the orbit of Mercury. By measuring their velocities, scientists calculate a mass of several million suns confined within a volume smaller than our solar system. Nothing known to physics could contain such mass except a black hole. Its gravity shapes the motion of gas, dictates the orientation of nearby clouds, and defines the dynamic core of the galaxy. Similar results emerge from observations of neighbouring systems. In the galaxy known as Messier, 32 stars accelerate around a centre weighing millions of solar masses. In the giant elliptical Messier 87, an even larger black hole dominates its mass, reaching billions of suns. The correlation between galaxy size and central black hole mass is consistent and precise, suggesting that these objects grow together over time. The relationship is not static. The evolution of a galaxy and its central black hole appears to be intertwined through cycles of activity. When matter falls toward the centre, the region brightens across many wavelengths. Gas spirals inward, forming an accretion disk that glows as it heats. The resulting radiation can outshine all the stars in the host galaxy combined, creating what astronomers call an active galactic nucleus. In these moments, the galaxy's dark heart becomes a beacon visible across the cosmos. The energy released can drive winds and jets that push gas outward, influencing star formation and reshaping the galactic environment. When the supply of matter diminishes, the core dims again, entering a long quiet phase. This alternating rhythm between feeding and resting repeats over cosmic timescales, gradually building both the galaxy and its black hole. The mechanisms behind this growth are varied. Some galaxies merge with others, combining their central masses. Others draw material from interstellar clouds or tidally strip gas from nearby companions. As these processes continue, the gravitational balance of each system adjusts. The stars within respond slowly, altering their orbits to accommodate the changing mass distribution. Over billions of years, a galaxy's structure can transform entirely. A once spiral system may become an elliptical, its delicate arms erased by repeated mergers. Yet at the centre, the black hole endures, often growing even as the larger structure around it is torn apart. In this way, black holes serve as records of galactic history, marking the cumulative weight of all events that have shaped their hosts. The surrounding space is rarely still. Interstellar gas flows through each galaxy, sometimes condensing into stars, sometimes drawn toward the core. Magnetic fields, turbulence, and radiation all influence its motion. Near the centre, gravity dominates, funneling matter toward the inner regions where temperatures rise and velocities increase. The gas emits X-rays and ultraviolet light, betraying the presence of the gravitational engine at its core. These emissions vary over time, fluctuating with the rate of accretion. By studying such changes, astronomers can infer the structure of the inner flow, even though it remains hidden from direct view. Variability in this context is not noise but information, a sign of how matter behaves when approaching the limits of known physics. Not all galaxies are equally active. Many, like the Milky Way, contain dormant or weakly accreting black holes. Others, known as quasars, shine so brightly that they can be seen across billions of light-years. The difference lies mainly in the availability of material to consume. When fuel is plentiful, the gravitational energy released near the event horizon becomes immense. Photons scatter electrons, spiral along magnetic lines, and plasma escapes in narrow collimated jets. These processes connect the smallest measurable scales regions only light hours wide to the largest stretching thousands of light years. The black hole itself remains invisible, yet the patterns of light and motion around it form a clear signature. In these luminous states, the center of a galaxy becomes a miniature universe of its own, governed by extreme conditions that test the limits of theory and observation alike. The connection between a galaxy and its black hole extends beyond individual events. Large surveys reveal that nearly all mature galaxies host central black holes, and their masses scale roughly with the velocity of stars in the surrounding bulge. This indicates a deep coupling between stellar dynamics and the central gravitational well. The formation of stars, the distribution of heavy elements, and the cooling of interstellar gas all depend on the energy released by the active nucleus. Even when inactive, the presence of the black hole affects the orbits of stars in its vicinity, maintaining order in an otherwise chaotic environment. In this sense, black holes act as both anchors and regulators, stabilizing the systems they inhabit. From an observational standpoint, black holes transform galaxies into cosmic laboratories. Their influence can be traced through spectral shifts, emission lines, and gravitational lensing. Instruments like the Event Horizon Telescope resolve their silhouettes against glowing matter, revealing the outlines predicted by general relativity. Space observatories such as the Chandra X-ray Observatory and the James Webb Space Telescope capture complementary details mapping the hot and cold components of the galactic core. Together, these observations construct a unified picture. Galaxies are not merely collections of stars, but dynamic ecosystems organized around central gravitational wells. These wells, though silent, orchestrate processes that determine the fate of entire systems. Across cosmic distances, the story repeats. Galaxies collide and merge their central black holes, approaching each other in spiraling dances that last millions of years. When they finally coalesce, they emit bursts of gravitational waves, ripples in spacetime itself before settling into a new equilibrium. Each merger adds mass to the core and reshapes the surrounding structure, ensuring that no galaxy remains static. The universe is a continuous flow of formation, destruction, and rebirth, and black holes stand at the core of this rhythm. They represent not an absence, but a concentration of matter, energy, and time into singular regions that define the architecture of the cosmos. As the narrative moves deeper, the focus shifts from the galactic scale to the formation of these entities themselves. To understand how they arise, one must look to the lives and deaths of stars, where the conditions for gravitational collapse are first met and where the seeds of all later extremes are planted. Black holes appear in many forms, but all share the same defining feature: a region of space-time where gravity is so strong that nothing, not even light, can escape. Their diversity lies not in nature, but in scale. Astronomers classify them by mass and environment, recognizing three primary categories supported by observation, and one still theoretical. Each category tells a different story about how matter collapses, gathers, and evolves in the universe. From stellar remnants only a few times heavier than the Sun to supermassive cores weighing billions of solar masses, their range spans every order of magnitude, linking the smallest stellar processes to the largest galactic structures. Understanding this diversity begins with the smallest examples: the stellar mass black holes born from the death of massive stars. When a star at least several times heavier than the Sun exhausts its nuclear fuel, the outward pressure that once balanced gravity disappears. The core collapses inward, forcing protons and electrons to merge into neutrons. If the mass is below a certain threshold, a neutron star forms. If it exceeds that limit, collapse continues until no known force can halt it. The result is a black hole with a radius of only a few tens of kilometers, but a gravitational field strong enough to trap light. Such objects are scattered throughout galaxies, often hidden unless they interact with a nearby companion. When paired with another star, the black hole can draw material from its partner, forming an accretion disk that emits X-rays as gas spirals inward. These emissions allow astronomers to detect stellar black holes, indirectly identifying dozens within the Milky Way and many more in distant galaxies. The typical stellar black hole ranges from a few to a few tens of solar masses, but observations reveal an upper and lower gap in this distribution. Below about 3 solar masses, neutron stars prevail. Above roughly 50 stars may collapse entirely, without a visible supernova forming larger black holes in silence. These gaps provide clues about the physics of stellar evolution and the limits imposed by radiation pressure and metallicity, the fraction of elements heavier than helium within a star. In regions of low metallicity, such as the early universe or primitive galaxies, more massive stars can form and collapse directly into black holes, providing seeds for later growth. Between the stellar and the supermassive lies a curious and less understood class, the intermediate mass black holes. Their masses range from hundreds to hundreds of thousands of suns, bridging a gap once thought empty. Evidence for them comes from dense star clusters, where stars orbit an unseen center, or from ultraluminous X-ray sources that exceed the brightness expected from stellar systems. These candidates challenge models of formation because they cannot arise from single stellar collapse alone. One hypothesis suggests that repeated mergers of stellar black holes within crowded clusters could build up intermediate masses over time. Another proposes that gas clouds collapsing before star formation could create them directly. While evidence remains incomplete, ongoing searches using gravitational waves and high-resolution imaging continue to narrow the possibilities. The giants among black holes, the supermassive class, dominate the centers of galaxies. Their masses range from millions to billions of suns, their event horizons spanning regions larger than entire solar systems. The mechanisms that produce such immense objects remain subjects of study, but several channels are recognized. They may form from the merging of smaller black holes, the direct collapse of massive gas clouds in the early universe, or rapid accretion of matter over cosmic time. Observations show that by the time the universe was less than 1 billion years old, some quasars already hosted black holes exceeding 1 billion solar masses, implying that their growth must have been extraordinarily efficient. The challenge for astrophysics is to reconcile these early giants with the slower rates observed in the modern cosmos. Each class of black hole reveals something about its surroundings. Stellar black holes record the life cycle of stars. Intermediate ones mark the dynamics of clusters. Supermassive varieties trace the evolution of galaxies. They differ in scale, yet the physics that defines them is identical. The boundary known as the event horizon depends only on mass and spin. The greater the mass, the weaker the curvature of spacetime at the horizon, meaning that paradoxically the tidal forces near a supermassive black hole can be gentler than those near a smaller one. An astronaut approaching a stellar black hole would be stretched and torn long before reaching its horizon, while the same approach near a supermassive black hole could occur without immediate disruption. This simple scaling shows how size alters experience while preserving fundamental law. Observations across wavelengths reveal further distinctions. Stellar black holes, often in binary systems, emit strong X-ray and gamma-ray radiation when actively accreting matter. Intermediate black holes, if confirmed, would produce less frequent but more powerful bursts. Supermassive black holes generate radio jets, infrared emissions, and sometimes visible light from their energetic surroundings. Despite these differences, all reveal the same underlying process: gravitational energy converted into heat and radiation as matter descends toward the horizon. The efficiency of this conversion can exceed that of nuclear fusion making accretion onto black holes, one of the most powerful energy sources in the universe. Beyond the known classes lies a concept tied to the earliest moments after the Big Bang primordial black holes. These hypothetical objects would have formed not from stars but from density fluctuations in the infant universe, when matter was still a hot plasma. If regions of space became slightly denser than their surroundings, gravity could cause them to collapse before any stars existed. Depending on conditions, their masses could range from tiny fractions of a gram to thousands of suns. None have been confirmed, yet their existence remains possible within certain limits set by cosmic background observations and gravitational lensing surveys. If discovered, primordial black holes could help explain the nature of dark matter or illuminate how structure first emerged. Taken together, these categories outline a continuous spectrum of gravitational collapse. At one end lie the remnants of dying stars, at the other, the colossal engines at galactic cores. Between them, the boundaries blur as mass accumulates, merges, and transforms. Black holes thus serve as both endpoints and intermediaries, linking processes that span from individual stellar deaths to the shaping of galaxies themselves. Their study bridges disciplines uniting stellar astrophysics, high-energy physics, and cosmology under a single framework. The diversity of black holes is mirrored in the diversity of tools used to observe them. X-ray observatories trace accretion flows, radio arrays map jets, infrared telescopes peer through dust to reveal hidden cores. Gravitational wave detectors capture their collisions, turning spacetime itself into a means of observation. Each method provides a different view of the same underlying reality, that these objects are not isolated anomalies but integral components of the cosmic order. They mark transitions, boundaries, and continuities within a universe defined by change. As the path of exploration narrows further inward, attention turns from classification to formation. The next step lies in the life cycle of massive stars, the factories of the elements and the cradles of the smallest black holes, where the conditions for gravitational collapse are first set in motion and where the seeds of the universe's most extreme objects are born. The story of a black hole begins within the heart of a massive star. For most of its life, a star exists in balance between two opposing forces, the inward pull of gravity and the outward pressure produced by nuclear fusion in its core. Hydrogen fuses into helium, releasing energy that radiates through the star's layers and outward into space. This balance can last millions of years, but it is temporary. As the star consumes its fuel, the reactions that sustain it begin to slow. When the hydrogen at its center is exhausted, fusion shifts to helium, and then to heavier elements in successive stages, each shorter than the last. In the most massive stars, fusion continues until the core becomes iron. At this point, no further energy can be extracted from fusion because iron's nucleus is too stable. Without outward pressure to counter gravity, the core collapses. The fall is rapid and violent, compressing matter to densities beyond imagination. As the core contracts, temperatures soar to billions of degrees. The outer layers, suddenly unsupported, rush inward, rebound against the dense core, and blast outward in an enormous supernova explosion. This brief moment releases more energy than the star produced over its entire lifetime. What remains at the center depends on mass. If the collapsing core contains up to about 2 or 3 times the mass of the Sun, it stabilizes as a neutron star composed almost entirely of neutrons, packed together in a single giant atomic nucleus. But if the mass exceeds this limit, gravity overwhelms all resistance. The collapse continues until spacetime itself curves inward beyond return. The event horizon forms marking the birth of a black hole. Stellar black holes are born from this collapse in various environments. Some emerge within dense stellar clusters where massive stars are common. Others form in binary systems where one star evolves faster than its companion. When the first star collapses into a black hole, its partner may later feed it gas, or eventually merge with it, forming a heavier remnant. Over cosmic time, such interactions contribute to the slow accumulation of more massive black holes. Supernova remnants observed through X-rays and radio waves often hint at these hidden cores. The expanding gas clouds reveal where explosions occurred, while the motions of nearby stars trace the invisible gravitational center left behind. The physics of collapse remains one of the most challenging frontiers in astrophysics. As the core compresses, matter reaches densities beyond those achievable in any laboratory. Neutrons are squeezed so tightly that their internal structure, composed of quarks and gluons, may begin to dissolve. The behavior of such matter, sometimes called quark-gluon plasma, is not fully understood. The boundary between a neutron star and a black hole thus marks not only a gravitational threshold, but also a limit in our knowledge of particle physics. General relativity describes how spacetime behaves under extreme curvature, but it does not explain what happens at the singularity where density becomes infinite. The current theories fail, suggesting the need for a unified description that merges gravity with quantum mechanics. The collapse of a massive star does more than create a black hole, it also drives cosmic evolution. Supernova scatter heavy elements into space, enriching the interstellar medium from which new stars and planets form. The black hole that remains is silent but persistent, slowly influencing its surroundings. If part of a binary system, it may draw in gas from its companion, creating a bright X-ray source. If isolated, it moves through space nearly undetectable, except through its gravitational pull. Simulations suggest that our galaxy alone could contain hundreds of millions of such remnants. Most are dormant, wandering unseen between the star's relics of earlier generations of stellar life. Observations of supernovae provide a glimpse into the process of collapse in real time. Telescopes detect flashes of light and bursts of neutrinos, nearly massless particles that escape from the core before light does. In some cases, the explosion fails to appear, suggesting that the star has imploded directly into a black hole without a visible outburst. Such events, known as failed supernovae, reveal the subtle balance between explosion and collapse. By monitoring nearby galaxies, astronomers have identified stars that simply vanish from view, their disappearance marking the quiet formation of new black holes. The fate of collapsing stars also depends on environment. In galaxies with low metallicity, massive stars lose less material through stellar winds, allowing them to retain more mass until death. These stars are more likely to collapse directly into black holes, producing heavier remnants than those found in metal-rich regions like the Milky Way. Early in the universe's history, when heavy elements were scarce, such conditions were common. As a result, the first generations of stars, sometimes called population 3 stars, may have created the earliest stellar black holes seeding the young universe with the building blocks of later supermassive ones. In binary systems, the interplay between two massive stars adds complexity. As one star evolves and expands, its outer layers can be drawn toward its companion. When one eventually collapses into a black hole, it may remain gravitationally bound to the other. Over time, the orbit tightens as gravitational waves carry energy away. The two objects spiral inward until they merge, releasing a final burst of gravitational radiation detectable across vast distances. Such events have now been observed, directly confirming that stellar black holes not only form, but also evolve through collisions. Each merger produces a remnant slightly smaller in total mass than the sum of its parts, the difference radiated away as energy. The remains of these stellar deaths populate galaxies like unseen fossils. Some lie dormant for eons, while others continue to grow through accretion. In the densest star clusters, repeated collisions may drive runaway growth, forming intermediate mass black holes. Over cosmic time, these may sink toward galactic centers, merging into still larger bodies. In this way, the death of individual stars contributes to the growth of structures millions of times their size. Gravity, acting patiently across billions of years, builds the universe's hierarchy from small beginnings. From an observational perspective, the collapse of stars into black holes is a process reconstructed through many forms of light. X-ray satellites reveal accreting binaries. Optical telescopes track supernova remnants. Gravitational wave detectors capture the merging echoes of their remnants. Each signal carries part of the story, and together they form a consistent picture. Stars die, matter falls, and gravity prevails. The outcome is not destruction, but transformation, the conversion of luminous matter into a gravitational well that persists indefinitely. The universe contains countless such transformations, each silent after the initial burst. These remnants, though invisible, remain part of the cosmic balance. Around them orbit stars, planets, and gas clouds, all drawn by forces they cannot see. Their existence reminds us that every black hole begins not as an abstract idea, but as the end of a star, a transition from light to darkness, from motion, sustained by fusion, to stillness, maintained by gravity alone. The next region of exploration lies beyond the stellar scale in the intermediate range, where many such remnants combine, forming larger bodies that bridge the gap between individual stars and the enormous centers of galaxies. Between the smallest remnants of dying stars and the colossal cores of galaxies lies a hidden class of objects that bridge the scale between the two. These are the intermediate mass black holes, the quiet midpoints in the cosmic hierarchy. Their masses range from a few hundred to a few 100,000 times that of the Sun. For decades their existence was uncertain, too large to be born from a single collapsing star, too small to power the luminous centers of galaxies. They occupy an observational gap that challenges both theory and detection. Yet evidence continues to grow that these objects are real, residing in places where gravity gathers matter, but light remains faint. Understanding them provides a vital link in tracing how the universe builds its largest black holes from its smallest beginnings. The first hints came from dense stellar clusters scattered throughout galaxies. In some of these clusters, stars near the center move faster than expected, suggesting the presence of an unseen mass. These clusters, ancient and compact, are relics of the early universe, each containing hundreds of thousands of stars. Their internal dynamics are governed by countless gravitational interactions where heavy stars sink toward the core and lighter ones drift outward. Over billions of years, collisions and mergers among massive stars can produce one or more black holes. If the environment is dense enough, these remnants can merge repeatedly, growing step by step into an intermediate mass range. This process, called runaway collapse, is supported by computer simulations and partially by observation, though direct proof remains elusive. One of the most intriguing candidates lies in the cluster known as Omega Centauri, located within the Milky Way. Measurements of stellar motions there hint at a central object, with a mass tens of thousands of times that of the Sun. Similar clues have been found in other clusters both within and beyond our galaxy. Another source of evidence comes from ultraluminous X-ray sources observed in nearby galaxies. These points of light shine more brightly than typical stellar binaries, but less than active galactic nuclei. Their brightness implies accretion onto a black hole, larger than a stellar remnant but smaller than a supermassive one. When such a system captures material from a companion star or surrounding gas, the infalling matter heats and emits radiation at intensities best explained by an intermediate mass object. Despite these clues, confirmation remains difficult. Intermediate mass black holes are faint by nature. They lack the enormous accretion disks of quasars and the frequent flaring activity of smaller X-ray binaries. Their gravitational reach is modest, affecting only the innermost regions of their host clusters. Detecting them requires exquisite precision in measuring stellar velocities and light curves. Instruments such as the Hubble Space Telescope and large ground-based observatories, equipped with adaptive optics, have pushed these limits, offering indirect but persuasive indications. More recently, gravitational wave observatories have begun to detect mergers involving objects heavier than typical stellar black holes, hinting that at least some intermediate masses do exist. Theoretical models suggest several possible paths to their formation. The first involves repeated mergers within dense stellar clusters, a slow and cumulative process that could build a central object over time. The second envisions the direct collapse of massive gas clouds early in cosmic history before stars even form. In this scenario, regions of gas several thousand solar masses in size could collapse under gravity if cooling processes are inefficient. The third possibility connects to the remnants of population 3 stars the first generation formed after the Big Bang. These primordial giants, perhaps hundreds of times heavier than the Sun, may have left behind black holes, large enough to serve as seeds for later intermediate mass objects. Each pathway highlights a different era of cosmic evolution, linking stellar physics, galactic formation, and cosmology into a single chain of development. If intermediate mass black holes are common, they may play a crucial role in shaping galaxies. They could act as gravitational anchors within small dwarf galaxies or the remnants of early galactic fragments. When these fragments merge over time, their central black holes may combine as well, giving rise to the supermassive ones seen today. This hierarchical growth model aligns with observations that galaxies evolve through mergers gradually assembling larger structures from smaller precursors. Intermediate mass black holes thus serve as the missing intermediaries connecting the deaths of the first stars to the active cores of modern galaxies. Observations of dwarf galaxies lend some support to this idea. Several such galaxies display signs of faint compact sources emitting X-rays and radio waves consistent with low-level accretion onto intermediate mass black holes. These galaxies, small and relatively simple, provide natural laboratories for studying early stages of black hole evolution. Unlike giant galaxies where activity is dominated by massive nuclei dwarfs, preserve conditions similar to those of the young universe, allowing astronomers to trace processes that once occurred on a larger scale. Through careful measurement of their luminosity and gas dynamics, scientists infer central masses that fall squarely within the intermediate range. The challenge lies in distinguishing these objects from alternative explanations. Dense clusters of neutron stars or stellar remnants can mimic some of their effects, as can complex gas flows or observational limitations. To confirm an intermediate mass black hole, one must rule out all other possibilities and measure a gravitational influence consistent only with a single massive body. The precision required makes each candidate a subject of long-term study, often spanning decades. As technology improves, so too does the ability to detect subtle motion and faint radiation that betray their existence. Intermediate mass black holes may also hold clues about the production of gravitational waves. When two of these objects merge, they produce signals of lower frequency than those generated by smaller black holes, but higher than those expected from supermassive collisions. Detecting such signals requires space-based detectors capable of sensing minute distortions over vast distances. Missions like the planned Laser Interferometer Space Antenna aim to capture these intermediate events, potentially confirming a whole population of hidden black holes that cannot be seen by light. Such discoveries would provide the missing link between the stellar mergers already observed and the distant titanic coalescences expected at galactic centers. The existence of intermediate mass black holes also affects how astronomers interpret the early universe. If they formed soon after the first stars, they could have influenced the rionization of cosmic gas by emitting radiation during their brief active phases. They may have also served as seeds for the earliest quasars, accelerating the appearance of supermassive black holes in galaxies that existed when the universe was still young. Their presence would help explain how such enormous objects appeared so quickly after the Big Bang. Even if rare, their combined impact could have left subtle imprints on cosmic background radiation and large-scale structure formation. As research continues, these elusive mid-sized black holes remind scientists that cosmic evolution operates across a continuous spectrum. There is no single threshold where one class ends and another begins. Matter collapses, merges, and accumulates under gravity's patient guidance, building ever larger structures from simple beginnings. Each scale mirrors the next bound by the same physical laws, but expressed in different magnitudes. The study of intermediate mass black holes thus bridges the personal and the cosmic, linking the brief life of a star to the vast architecture of galaxies. Moving inward from this midpoint, attention turns next to the giants of the cosmos, the supermassive black holes, whose gravity defines the hearts of galaxies, and whose presence illuminates the extremes of energy and scale. At the centers of galaxies, hidden behind dense clouds of dust and gas, lie the most massive black holes known to exist. These are the supermassive black holes, objects whose masses range from millions to billions of times that of the Sun. Their gravitational influence extends far beyond their event horizons, shaping the motion of stars, the distribution of gas, and even the long-term structure of their host galaxies. Unlike the smaller stellar remnants formed from the death of individual stars, these immense entities represent a culmination of countless processes operating over cosmic time. They are both ancient and active, silent and yet capable of releasing energies that rival entire galaxies. Understanding them means tracing the slow, persistent work of gravity as it sculpts matter into the largest stable configurations known. The presence of supermassive black holes is now established in nearly all large galaxies. Their existence was inferred long before they were directly observed through the motions of stars orbiting at tremendous speeds near galactic centers. In our own Milky Way infrared observations track individual stars completing orbits around a single invisible point, with a mass of about 4 million suns. The precision of these orbits leaves little doubt the mass is concentrated within a region smaller than the orbit of Mercury, an impossibility for any known form of matter except a black hole. In other galaxies, particularly those farther away, astronomers measure the velocities of gas and the brightness of energetic emissions to estimate central masses. The relationship between the mass of a galaxy's bulge and its black hole is consistent across a vast range of systems, implying a fundamental link between galactic growth and central gravity. The question of how these giants form remains open, but is guided by several leading theories. One possibility is that they begin as the remnants of the first massive stars growing steadily through the accretion of gas and the merger of smaller black holes. Over billions of years, these processes could build the supermassive scales seen today. Another hypothesis proposes that certain dense gas clouds in the early universe collapse directly into black holes without first forming stars. Such direct collapse models explain how quasars with billion solar mass black holes could appear less than 1 billion years after the Big Bang. A third pathway combines both ideas. Early stellar black holes merge into intermediate masses, which then act as seeds for runaway growth when conditions permit efficient accretion. The reality may involve all of these routes operating at different times and environments, producing the variety of black holes now observed. Once formed, a supermassive black hole can grow through accretion, the steady inflow of matter drawn by gravity. As gas spirals inward, friction heats it to millions of degrees, producing radiation across the electromagnetic spectrum. The resulting brightness can outshine the combined light of all stars in the host galaxy, creating what astronomers call an active galactic nucleus. In its most extreme state, such an object is seen as a quasar, a point-like beacon visible across billions of light-years. Quasars serve as cosmic lighthouses, marking the positions of growing, supermassive black holes in the early universe. Their energy output, though vast, does not come from the black hole itself, but from the gravitational potential energy released by matter before it crosses the event horizon. The conversion efficiency is remarkable. Up to 10% of the infalling matter's rest mass can become radiation, compared with less than 1% for nuclear fusion inside stars. As matter accumulates, feedback processes arise that regulate the growth of both black hole and galaxy. The intense radiation from accretion can heat surrounding gas or drive winds that push material outward, limiting further feeding. This self-regulating mechanism may explain why black hole mass correlates so closely with galactic bulge properties. In giant elliptical galaxies, such feedback maintains a delicate equilibrium, preventing excessive star formation and stabilizing the system. In spiral galaxies like the Milky Way, the central black hole spends most of its time dormant, punctuated by brief episodes of activity when new material becomes available. These cycles of feeding and quiescence shape the appearance and evolution of galaxies over cosmic timescales. Some supermassive black holes exhibit another remarkable feature: relativistic jets. These narrow beams of plasma shoot out from regions near the poles of the black hole at speeds approaching that of light. They extend across thousands of light-years, emitting radio waves and high-energy particles into intergalactic space. The exact mechanism behind their formation involves strong magnetic fields anchored in the accretion disk. As the black hole's rotation twists these fields, they channel part of the inflowing matter outward along the axis of spin. The resulting jets can influence the temperature and density of gas far beyond the host galaxy, shaping its surroundings on scales measured in millions of light-years. The first direct image of a supermassive black hole's shadow, released by the Event Horizon Telescope, confirmed the predictions of general relativity. Observations of the galaxy Messier 87 revealed a bright ring of emission surrounding a dark central region, the projected silhouette of the event horizon. The size and shape of this shadow matched theoretical expectations for a rotating black hole. Later, the same technique was used to image Sagittarius A at the center of the Milky Way, further verifying that such objects exist not only in distant galaxies but also in our own. These achievements mark one of the great milestones of modern astronomy, the transition from inference to direct observation. The environments around supermassive black holes are extraordinarily complex. Matter falling inward forms a turbulent accretion disk composed of gas dust and magnetic fields. Temperatures vary from millions of degrees near the inner edge to only a few thousand farther out. Within this disk, friction, turbulence, and magnetic reconnection convert gravitational energy into heat and radiation. photons scatter, electrons accelerate, and particles interact in ways that probe the limits of known physics. Above and below the disk, magnetic fields can lift material outward, creating the corona and launching jets. The balance between inflow and outflow determines how efficiently the black hole gains mass and how much energy escapes into space. Supermassive black holes are not static. Over time, galaxies merge, bringing their central black holes closer together. These pairs orbit each other for millions of years before merging in a final powerful burst of gravitational waves. Such mergers may contribute significantly to the population of the largest black holes, and their detection through future space-based observatories will open a new window onto galactic evolution. The ripples they produce travel across the cosmos, carrying information about masses, spins, and distances, revealing the hidden architecture of merging galaxies. Despite their names, supermassive black holes do not simply consume. They participate in the cosmic cycle of matter returning energy to their surroundings in ways that sustain structure. Their radiation can trigger star formation in compressed gas clouds or halt it by dispersing material. Their jets enrich intergalactic space with elements forged in stars, spreading the raw material for new systems. In this sense, they serve as engines of balance, converting gravitational collapse into radiant order. The processes that occur around them define some of the universe's brightest phenomena, yet at the core remains absolute darkness, a region where space-time curves inward beyond the reach of light. The study of these immense entities continues to reveal the unity of scale in the cosmos. From stellar remnants to galactic cores, the same physical laws govern behavior. Gravity remains constant, bending space and dictating time, while matter and energy respond in predictable patterns. As attention now moves inward, the focus turns from the formation and growth of black holes to their role within galaxies, how their energy, magnetism, and motion influence the stars, gas, and cosmic webs that surround them. Long before galaxies matured and settled into familiar shapes, the early universe may have seeded the first black holes in a way that differed entirely from the collapse of stars. These hypothetical primordial black holes belong to an ancient era, forming not from stellar death, but from the conditions present only moments after the Big Bang. In those first fractions of a second, matter and energy were intertwined in a hot, dense plasma where quantum fluctuations created small variations in density. Most of these irregularities expanded harmlessly with the rest of the universe, but if some regions grew dense enough, their gravity could overcome the outward expansion and collapse directly into black holes. These primordial remnants, if they exist, would have formed when the universe was still less than a second old, long before the first stars lit their nuclear fires. Theoretical models predict a vast range of possible masses for such objects, depending on when they formed. Those collapsing earliest would be tiny, perhaps no heavier than a mountain, while those forming slightly later could be thousands or even millions of times the mass of the Sun. Smaller ones would have evaporated quickly through a process known as Hawking radiation, losing energy over time and disappearing within the first billion years. Larger ones could still exist today, hidden among the dark matter that fills galaxies. Despite decades of searching, none have been conclusively identified, yet their potential significance keeps them central to cosmological research. They could explain certain gravitational lensing events, contribute to dark matter density, or serve as the initial seeds from which supermassive black holes later grew. The search for primordial black holes involves indirect methods because their signals would be faint. Astronomers look for gravitational microlensing, a temporary brightening of a distant star caused when a compact object passes in front of it and bends its light. Large surveys of the sky have placed limits on how common such objects can be in various mass ranges, narrowing the possibilities but leaving open several small windows where they might still exist. Another approach comes from gravitational wave detections. Some observed mergers involve black holes that are difficult to explain through normal stellar evolution, suggesting they could have primordial origins. The pattern of merger masses, spins, and frequencies may eventually reveal whether a hidden population of ancient black holes contributes to the signals now recorded across the universe. If primordial black holes do exist, their influence would extend beyond gravity alone. During the early epochs of cosmic history, their radiation and interactions could have affected the distribution of matter and the formation of the first galaxies. Some theories propose that they played a role in reheating the universe after the cosmic dark ages, or in generating fluctuations that seeded later structures. Even their absence in observations provides valuable information, helping cosmologists refine models of inflation, the rapid expansion that followed the Big Bang. Each constraint rules out certain conditions of the early universe, guiding researchers toward a more precise understanding of how matter and energy evolved into the cosmic web we observe today. The concept of primordial black holes also challenges assumptions about the nature of spacetime itself. The equations of general relativity permit their formation under extreme conditions, but combining these equations with quantum theory suggests that spacetime at such densities might behave differently than predicted. Some models propose that instead of forming a singularity, a point of infinite density, a collapsing region could stabilize into a compact but finite object governed by quantum effects. Such possibilities remain speculative, yet they highlight how primordial black holes sit at the intersection of cosmology, particle physics, and quantum gravity, connecting the smallest scales of matter with the largest scales of the universe. The notion that some black holes could predate galaxies changes how astronomers view cosmic evolution. Instead of forming only after the first stars, black holes might have been present from the beginning, shaping the growth of matter around them. A primordial black hole embedded within a dense region of gas could act as a gravitational seed drawing material toward it and accelerating the formation of galaxies. This idea provides one explanation for the appearance of massive quasars at very early times, objects that seem too large to have grown so quickly by ordinary means. By serving as early anchors, primordial black holes could bridge the gap between the physics of the Big Bang and the first observable structures in the universe. Testing these ideas requires instruments sensitive to both the smallest and largest phenomena. Cosmic microwave background experiments search for traces of early black hole evaporation, which would have released bursts of high-energy particles. X-ray and gamma-ray telescopes monitor the sky for faint emissions consistent with such decay. Meanwhile, large-scale surveys map gravitational lensing effects across millions of galaxies, measuring subtle distortions that could betray the influence of unseen masses. Future missions, particularly those observing gravitational waves at low frequencies, may detect mergers of black holes formed in the early universe, distinguishing them from those of later stellar origin. Though the evidence remains circumstantial, the possibility of primordial black holes continues to shape theoretical work. Their existence would simplify several mysteries simultaneously: the presence of supermassive black holes in young galaxies, the nature of dark matter, and the limits of early universe physics. Their absence would be equally informative, confirming that all known black holes arise from stellar and galactic processes. Either outcome enriches our understanding of how the cosmos transforms energy into structure, and structure into complexity. In the broader cosmic landscape, primordial black holes, whether real or hypothetical, represent a profound idea that gravity may have sculpted darkness before light itself emerged. Their imagined existence stretches the timeline of black holes to the very beginning of time, linking the origin of matter with the formation of the most extreme objects known. While no telescope has yet captured their signal, the framework of modern physics keeps the door open for the universe, often hides its oldest secrets in silence. As the exploration moves inward from the earliest epochs, toward the environment shaped by black holes, we can observe the focus now turns to how these massive entities grow. Through the accumulation of matter and the merging of smaller companions, black holes transform from stellar remnants or primordial seeds into cosmic giants, their evolution spanning billions of years and influencing everything within their reach. Growth defines the life of a black hole. Though it begins as a collapse, its existence afterward is one of slow accumulation and transformation. Gravity ensures that nothing massive remains truly isolated. Gas dust radiation and even stars drift inexorably toward regions of higher gravitational potential. Around a black hole, this pull becomes irresistible. Over cosmic timescales, black holes increase their mass through two main pathways: accretion of surrounding material and mergers with other compact objects. Each process leaves distinctive marks on their environments, altering the temperature, luminosity, and structure of entire systems. Understanding how black holes grow connects the smallest stellar remnants to the largest supermassive bodies at galactic centers. Accretion begins when gas enters the gravitational sphere of influence surrounding a black hole. Instead of falling directly inward, the gas usually possesses angular momentum that causes it to orbit, forming a flattened structure known as an accretion disk. Friction within the disk converts gravitational energy into heat-raising temperatures to millions of degrees. As matter spirals inward, it radiates energy across the electromagnetic spectrum from X-rays to visible and radio waves. This radiation represents a kind of balance. While the black hole gains mass, it also loses potential energy as light. The rate at which this occurs is limited by the Eddington luminosity. The point at which radiation pressure outward equals the gravitational pull inward. If a black hole attempts to accrete faster than this limit, the intense radiation pushes material away, self-regulating its growth. The efficiency of accretion depends on the black hole's spin and the properties of its surroundings. A rapidly spinning black hole can drag spacetime around with it, allowing matter to orbit closer to the event horizon before crossing it. The deeper the fall, the more energy is released, making accretion onto rotating black holes among the most efficient energy conversion processes in the universe. In active galaxies and quasars, these mechanisms generate luminosities that can exceed 1 trillion times that of the Sun. Even when a black hole appears quiescent, as in the center of the Milky Way, it continues to gather small amounts of interstellar gas, growing imperceptibly year by year. The second pathway of growth mergers arises naturally in a universe where galaxies themselves collide. When two galaxies approach, their stars mostly pass without direct impact, but their dark matter halos and central black holes interact gravitationally. Over millions of years, the black holes spiral toward one another, losing orbital energy through gravitational radiation. As they draw closer, they form a binary system, eventually merging in a final burst of gravitational waves. These waves propagate across space, carrying information about the masses and spins of the merging objects. Observations of such events by instruments like the Laser Interferometer, Gravitational Wave Observatory and Virgo confirm that mergers between stellar mass black holes occur frequently. The same principles apply on larger scales for supermassive pairs, though the timescales involved are far longer. Galactic mergers are common in the universe's history, especially during its first few billion years. Images from space telescopes reveal galaxies caught in the act of colliding their shapes, distorted by tidal forces and their centers glowing with renewed activity. These interactions feed gas toward the nuclei, triggering bursts of star formation and accelerating black hole growth. As two central black holes spiral together, their gravitational influence stirs the surrounding stars and gas, ejecting some material and concentrating the rest. When the merger finally completes, the resulting black hole is more massive and often spinning rapidly from the combined angular momentum of its progenitors. The energy released during such events can heat the surrounding, gas prevent cooling, and alter the course of galactic evolution. Over billions of years, this cycle of feeding and merging creates a hierarchy of black holes connected across scales. Stellar black holes grow into intermediate ones within dense clusters. These in turn migrate toward galactic centers and contribute to forming the supermassive giants. The process is cumulative and self-similar. The same laws governing small-scale accretion apply at larger scales, though the timescales expand from thousands to billions of years. Even as black holes grow, they remain a small fraction of the mass of their host galaxies, yet their influence extends far beyond their size. A supermassive black hole may account for less than 1/1000th of its galaxy's total mass, but it can regulate the formation of stars across hundreds of thousands of light years. Observational evidence supports this interconnected growth. Surveys show that periods of high quasar activity coincide with epochs of intense galaxy formation, suggesting a shared source of fuel. When galaxies contain ample cold gas, both stars and black holes grow rapidly. As the gas is depleted or heated by feedback from active nuclei, growth slows, and galaxies mature. This feedback loop shapes the overall population of galaxies visible today. Elliptical galaxies, often formed from mergers, tend to host massive black holes and exhibit little ongoing star formation. Spiral galaxies, by contrast, maintain moderate central masses and sustain star formation in their disks. Thus, black hole evolution and galactic morphology are inseparable aspects of the same cosmic process. Beyond direct accretion and mergers, black holes may also capture and absorb compact objects such as neutron stars or smaller black holes. Each capture adds a small increment to the total mass and modifies the spin of the primary. These events also produce gravitational waves which, when detected, allow astronomers to infer how frequently black holes grow through such encounters. In dense star clusters, repeated interactions can lead to runaway mergers forming heavier remnants that may serve as seeds for future supermassive systems. Such processes illustrate how gravity acting locally through countless small steps produces the grand structures observed on cosmic scales. The balance between growth and feedback is delicate. Too much accretion can strip a galaxy of its cold gas-halting star formation and leaving behind an inert system. Too little and the central black hole remains underdeveloped, failing to stabilize its surroundings. Observations suggest that galaxies evolve toward equilibrium states, where the energy released by accretion matches the energy required to maintain thermal balance in their interstellar medium. This self-regulating principle ensures that despite the violent appearance of black holes, their long-term influence contributes to order rather than chaos. While gravity drives growth, the universe's expansion imposes limits. As space stretches, galaxies move farther apart, reducing the frequency of mergers and the availability of new material. In the far future, when star formation ceases and gas becomes scarce, black holes will continue to grow slowly by consuming what remains. Over incomprehensible spans of time, they may become the last significant structures isolated within an ever-darkening cosmos. Yet even then, they are not eternal. On the longest timescales, theoretical models predict that black holes will gradually lose mass through quantum processes, evaporating into faint radiation until only the memory of their existence remains. For now, however, growth defines their story. Each photon emitted from an accretion disk, each ripple of gravitational waves, and each disturbed cloud of interstellar gas speaks to the same underlying process, gravity's quiet persistence. From the collapse of single stars to the merger of entire galaxies, black holes accumulate the universe's history within their invisible boundaries. The next step in this inward journey explores how these giants once formed and fed, extend their influence outward again, shaping their galaxies through feedback jets and radiation that travel across space, linking the unseen heart of gravity with the luminous patterns of the cosmos. The influence of black holes extends far beyond the space immediately surrounding them. Though they trap all light within their event horizons, the energy released from matter before it crosses that boundary radiates outward across vast distances, shaping the structure and evolution of entire galaxies. This outward flow of energy is known as feedback, a process that connects the growth of black holes with the regulation of star formation and the behavior of interstellar gas. Without such feedback, galaxies might form stars too quickly, exhausting their gas reserves in short bursts. With it, the balance of creation and restraint persists for billions of years, ensuring the long-term stability of galactic systems. Feedback begins in the accretion disk, where matter spirals inward under extreme compression. As particles collide and heat, radiation exerts pressure that pushes back against gravity. In some regions, magnetic fields channel gas away from the disk's surface, forming winds that blow outward at thousands of kilometers per second. These winds carry mass momentum and energy into the surrounding medium. When they collide with cooler gas clouds farther out, they compress or disperse them depending on their strength. This interaction determines whether new stars will form or existing ones will be stripped of their raw material. Over time, such cycles of inflow and outflow sculpt the appearance and composition of a galaxy. The energy involved in this process is enormous. A supermassive black hole accreting near its maximum rate can release energy equivalent to the total luminosity of billions of stars. Although only a small fraction of this energy couples directly to the surrounding gas, even that fraction can have dramatic effects. Observations of distant galaxies show cavities and shock fronts in hot interstellar gas that align with the directions of radio jets, evidence that black holes inject energy into their surroundings. These features, seen in systems such as the Perseus cluster and the elliptical galaxy Messier 87, confirm that black holes act as engines regulating the temperature and density of the galactic core. Two primary forms of feedback operate depending on the state of accretion. The first, often called quasar-mode feedback, occurs when the black hole is actively feeding and producing intense radiation. During these luminous phases, winds and radiation pressure drive powerful outflows that can sweep gas from the central regions of the galaxy, halting star formation temporarily. The second form, known as radio mode feedback, appears in less active but longer-lasting states. Here, relativistic jets powered by magnetic fields transport energy far from the nucleus into the surrounding halo-inflating bubbles of hot plasma that prevent the cooling of intergalactic gas. Both modes serve to stabilize the galactic environment, balancing the tendency toward collapse with gentle heating and motion. The scale of influence extends well beyond the visible galaxy. In clusters of galaxies where hundreds or thousands of members share a common halo of hot gas, central black holes in the dominant galaxies can affect the thermal state of the entire cluster. Observations with X-ray telescopes reveal cavities in the intra-cluster medium, vast dark voids where jets from the central black hole have displaced gas. These bubbles rise buoyantly, distributing energy through the cluster and preventing the gas from cooling too rapidly. Without this continual input, the gas would condense and form stars at unsustainable rates. Thus, even a single black hole occupying a region smaller than the solar system can govern the behavior of matter across millions of light years. Feedback not only regulates but also enables growth. In some circumstances, the compression caused by outflows triggers the formation of new stars by squeezing nearby gas clouds. This dual role, both suppressing and stimulating star birth, illustrates the complexity of black hole influence. The result is a self-regulating ecosystem, where energy released by accretion maintains equilibrium. Galaxies do not evolve through destruction or chaos, but through cycles of adjustment. The visible patterns of spiral arms, starbursts, and quiescent cores all trace back in part to the unseen dynamics of their central masses. Evidence for this relationship continues to strengthen through observation. Surveys show that galaxies with active nuclei often exhibit large-scale outflows detected in ionized gas and molecular lines. The velocities and geometries of these outflows correspond to theoretical predictions of feedback from accretion disks and jets. Infrared and radio observations reveal how dust and gas respond to such activity, sometimes clearing central cavities that expose the nucleus, and sometimes forming dense rings where new stars arise. Each case reflects a moment within a long continuum of interaction between a black hole and its host. On smaller scales, within tens of light years of the event horizon, the physical mechanisms that launch feedback become more intricate. Magnetic fields near the accretion disk twist and reconnect, transferring energy to surrounding plasma. Particles accelerate to relativistic speeds, creating synchrotron radiation observable at radio frequencies. These processes, though occurring in tiny regions compared to the galaxy, as a whole drive phenomena that influence structures thousands of times larger. The link between microphysics and cosmic architecture is continuous turbulence. In a plasma ring becomes pressure in a galactic wind, and that pressure becomes the sculptor of stellar distribution across generations. Black hole feedback also shapes chemical evolution. By expelling gas enriched with elements produced in previous generations of stars, it redistributes heavy elements throughout the galaxy and beyond. Intergalactic space, once nearly pure hydrogen and helium, now contains traces of carbon, oxygen, and iron carried outward by these processes. The next generation of stars forms from this enriched material, incorporating elements essential for planets and eventually for life. In this indirect way, the energy released by black holes participates in the wider story of cosmic chemistry, ensuring that the products of stellar fusion do not remain locked within galaxies but spread through the universe. The timescales over which feedback operates vary widely. A single episode of quasar activity might last a few million years, a brief moment in galactic history. Yet its consequences can persist for hundreds of millions of years as gas cools and redistributes. Over the lifetime of a galaxy, dozens of such episodes may occur, each reshaping its structure and luminosity. The rhythm of these cycles underlies the observed diversity of galaxies, from the blue star-forming spirals to the red quiescent ellipticals. Feedback provides the mechanism that turns isolated physical laws into coherent cosmic evolution. While much has been learned, many details remain uncertain. The efficiency with which black hole energy couples to gas, the exact geometry of winds and jets, and the interplay of magnetic fields and turbulence continue to be active areas of study. New observatories equipped with advanced detectors aim to map feedback in unprecedented detail, revealing how the smallest scales of gravity influence the largest visible structures. As this understanding deepens, the concept of the black hole shifts from that of a passive absorber to an active participant in the life of the universe. The journey inward now approaches the regions where these effects originate. Beyond the broad galactic scale, the focus narrows to the mechanisms inside the accretion disk itself. The flow's shocks and magnetic patterns that convert in falling matter into light motion and heat. The very engines that make feedback possible. Surrounding many black holes is a disk of material so dense and hot that it becomes one of the brightest phenomena in the universe. This structure, known as an accretion disk, forms as gas and dust spiral inward under gravity's pull. Instead of falling directly into the black hole, the material settles into a rotating flow flattened by angular momentum. Within this disk, matter rubs against itself, creating friction that converts gravitational potential energy into heat and radiation. The result is a continuous engine of energy release that powers quasars' active galactic nuclei and many X-ray sources in the cosmos. Though invisible beyond its event horizon, the black hole makes its presence known through this luminous process, which transforms invisible gravity into observable light. The physics of an accretion disk begins with motion and resistance. Gas drawn toward the black hole follows curved paths dictated by the warping of spacetime. The inner regions rotate faster than the outer ones, producing shear forces that generate heat. Microscopic turbulence and magnetic instabilities enhance this effect, transporting angular momentum outward so that mass can continue to move inward. This mechanism, known as viscous transport, ensures that material does not remain trapped in orbit, but gradually spirals closer to the event horizon. Temperatures rise dramatically as the gas compresses, reaching millions of degrees in the innermost zones. At such heat, atoms are stripped of their electrons, forming a plasma that glows across the electromagnetic spectrum. The appearance of an accretion disk depends on scale. Around stellar mass black holes, disks are compact, often only a few hundred kilometers across, radiating primarily in X-rays. Around supermassive black holes, the disks can span light days or even light years, shining in visible and ultraviolet light. Despite these vast differences in size, the governing equations remain the same. The disk's thickness is determined by the balance between pressure from radiation and the pull of gravity. In regions where radiation pressure dominates, the disk puffs outward, forming a geometrically thick but optically thin structure. Where gravity dominates, it remains thin and dense, producing efficient energy conversion. These variations create complex geometries that evolve over time as accretion rates change. Observationally, accretion disks reveal themselves through the light they emit and the way that light varies. Sudden increases in brightness, called outbursts, occur when instabilities in the disk cause temporary surges of infalling matter. The spectral shape of this emission provides information about temperature and density. X-ray telescopes detect rapid fluctuations corresponding to orbital motion near the innermost stable circular orbit, the last region where matter can orbit before plunging inward. By analyzing these variations, astronomers can infer properties such as spin and orientation, even though the black hole itself remains unseen. The patterns of variability act as fingerprints of the extreme physics taking place just outside the horizon. Magnetic fields play a central role in shaping the disk's behavior. As plasma moves and twists, it drags magnetic field lines along with it. In some configurations, these lines reconnect, releasing bursts of energy that heat the surrounding gas. In others, they form ordered structures that channel material away from the disk's surface, launching winds and jets. This interaction between gravity rotation and magnetism creates a self-sustaining dynamo that drives both accretion and outflow. The same process that feeds the black hole also powers the enormous jets that can extend for thousands of light years. The magnetic field acts as a bridge between small-scale turbulence and large-scale structure, binding the local physics of plasma to the cosmic architecture of galaxies. Near the inner edge of the disk, where space-time curvature is strongest, relativistic effects become dominant. Light emitted from this region experiences gravitational redshift, stretching its wavelength as it escapes the intense gravitational field. Time itself passes differently, here slowed relative to distant observers. The rotation of the black hole drags space-time around, with it causing matter to spiral inward in a process called frame dragging. These effects distort the appearance of the disk when viewed from afar. Instead of a simple circle, the disk appears lopsided, its inner edge brightened on one side by the relativistic beaming of light from matter moving toward the observer. High-resolution simulations and direct imaging, such as those from the Event Horizon Telescope, confirm these predictions, showing the distorted rings and shadows that trace the flow of energy near the event horizon. Accretion disks are not static structures. Their properties change as the available fuel fluctuates. When the supply of gas is abundant, the disk glows brightly, and the black hole experiences rapid growth. When the supply diminishes, the disk cools and thins, reducing emission to a faint whisper of radiation. Some systems alternate between these states in cycles lasting years or decades, reflecting changes in the surrounding environment. In binary systems where a black hole draws matter from a companion star, accretion can vary with the star's orbit, creating periodic bursts of light. On galactic scales, similar cycles may occur over millions of years as streams of gas flow toward or away from the central region. The energy released in these processes is staggering. A single gram of matter accreted onto a black hole can release nearly 10 times more energy than it would through nuclear fusion. Yet most of this energy never escapes as light. Some is trapped and carried inward, while some is converted into kinetic motion of jets and winds. This interplay between radiation and matter shapes the environment around every active black hole, controlling how much of the surrounding gas remains bound and how much is expelled. Over cosmic timescales, it is this balance that determines whether a galaxy grows fertile with stars or remains quenched and still. Observing accretion disks has required combining instruments across all wavelengths. X-ray observatories reveal the hottest regions, ultraviolet and optical telescopes capture the outer cooler zones, and radio arrays trace the extended structures formed by outflows. Polarimetry measurement of the orientation of light waves provides further insight, revealing how magnetic fields align and twist across the disk. Each technique contributes a different layer of understanding together, forming a coherent picture of one of nature's most efficient engines. The more closely scientists study these disks, the clearer it becomes that they are not peripheral features, but central players in the cosmic balance of energy. While theory describes the disk as a smooth, continuous flow, reality adds complexity. Simulations show turbulence, fragmentation, and shocks within the gas, producing flickering light and uneven jets. These irregularities may explain the variability seen in quasars and the intermittent nature of feedback in galaxies. The behavior of the disk depends sensitively on magnetic field, strength, chemical composition, and rate of inflow. No two accreting black holes are exactly alike, yet all follow the same physical principles. In this universality lies the beauty of the process. Simple laws of motion and energy create patterns of breathtaking diversity across the cosmos. As this exploration narrows further inward, it reaches the threshold where magnetic fields dominate and outflows, begin the region where matter, instead of continuing its descent, is accelerated outward in narrow beams moving at nearly the speed of light. These relativistic jets carry the influence of black holes far into space, linking the tiny regions near event horizons to the grand structures of galaxies and beyond. Above and below the blazing accretion disks of many black holes emerge narrow luminous columns of matter that reach across thousands or even millions of light years. These are relativistic jets, streams of plasma accelerated to speeds close to that of light, and confined by magnetic fields that twist and coil as they rise. They represent one of the most extraordinary forms of energy release in the universe, connecting the smallest scales of spacetime near the event horizon to structures visible across galaxies. Though the black hole itself remains dark, these jets make its presence known far beyond its gravitational reach. They demonstrate that even within regions defined by collapse and confinement, energy and motion can escape through complex interactions between gravity, rotation, and magnetism. The origin of these jets lies in the rotational energy of the black hole and its surrounding disk. As material orbits near the event horizon, magnetic field lines anchored in the disk are wound tightly by the immense rotational shear. This twisting stores energy that can be released when the field lines reconnect or open outward. Charged particles trapped in the magnetic field are accelerated along these lines, forming beams of plasma that shoot away from the poles. This mechanism, first described in theoretical form by the Blandford-Znajek process, extracts energy from the black hole's spin itself. The faster the rotation, the more power can be generated. In this way, the black hole functions as a kind of cosmic dynamo, transforming rotational energy into kinetic and electromagnetic output that shapes its environment on scales far exceeding its size. Observations reveal that relativistic jets are not uniform streams but layered and dynamic. The inner core moves at nearly light speed while surrounding sheath regions travel more slowly, interacting with the interstellar medium. Shocks within the jet create bright knots where particles are accelerated and radiation intensifies. These shocks occur when variations in velocity cause collisions within the flow, converting kinetic energy into light. The radiation emitted covers the entire electromagnetic spectrum from low-frequency radio waves to high-energy gamma rays. The strongest sources, known as blazars, are galaxies whose jets happen to point almost directly toward Earth, their emissions boosted by relativistic effects. The scale of these jets is staggering. Some extend far beyond the visible boundaries of their host galaxies, forming lobes of radio emission detectable across millions of light years. Within these lobes, the ejected material interacts with intergalactic gas, heating it and influencing future star formation. The energy carried by a single jet can equal or exceed the combined luminosity of all the stars in its galaxy, yet it originates from a region smaller than the solar system. This contrast in scale illustrates how black holes link the microscopic and the cosmic, translating quantum-scale processes into galactic phenomena through magnetic and gravitational coupling. Magnetic fields govern both the collimation and stability of the jets. Without them, the intense radiation and pressure near the black hole would scatter material in all directions. Instead, magnetic tension acts as an invisible scaffold, guiding plasma into narrow, coherent streams. The alignment and strength of these fields are determined by the rotation of the accretion disk and the spin of the black hole. High-resolution radio imaging using interferometry has revealed spiral patterns and polarization signatures that trace these fields in action. These observations confirm that magnetism, not purely gravity, dictates the geometry of the outflows. Where the magnetic field becomes unstable, jets can wobble, bend, or fragment, producing the complex morphologies seen in radio galaxies and quasars. The speed of jet particles approaches that of light, meaning time within the flow slows relative to the rest of the universe. From Earth, variations in brightness can appear to move faster than light itself, a visual illusion caused by the combination of high velocity and small angle of observation. This apparent superluminal motion, first detected in the 20th century, provided early proof that the jets were truly relativistic. Subsequent measurements of polarization and spectral lines have allowed astronomers to estimate particle energies and magnetic field strength, showing that these outflows carry both matter and electromagnetic energy in roughly equal measure. The impact of jets extends beyond the host galaxy. As they plow into intergalactic space, they create enormous cavities and shock waves. The hot plasma they deposit into the surrounding medium can prevent gas from cooling and collapsing into new galaxies, influencing the large-scale structure of the universe. In clusters of galaxies, pairs of opposite jets inflate vast bubbles within the intracluster medium, visible in X-rays as dark voids surrounded by bright rims of compressed gas. These cavities act as reservoirs of energy that maintain thermal balance in the cluster, echoing the feedback processes described earlier. Thus, jets serve as conduits through which black holes communicate with the cosmos, distributing energy and shaping evolution across scales unimaginable in human terms. The internal composition of jets remains a subject of study. Some may consist primarily of electrons and positrons, while others include heavier ions such as protons. The choice affects how the jets radiate and how they interact with external matter. Regardless of composition, the emission mechanisms are similar synchrotron radiation, from charged particles spiraling along magnetic fields and inverse Compton scattering where high-energy electrons boost lower-energy photons to gamma-ray levels. The balance of these processes produces the distinctive spectra observed from active galactic nuclei and blazars. These emissions fluctuate over time, reflecting the complex, often chaotic dynamics near the black hole. Numerical simulations now reproduce many aspects of jet formation and evolution. Using the equations of magnetohydrodynamics within the curved spacetime, described by general relativity scientists, model how plasma flows, how magnetic fields twist, and how energy is transferred outward. The results match observations with increasing precision, revealing that jet power depends strongly on the alignment between the black hole's spin and the magnetic field threading its horizon. When the two align, energy extraction is efficient and the jet remains stable. When misaligned, the flow becomes turbulent, producing intermittent bursts and changes in direction. These findings help explain the diversity of jet morphologies observed across galaxies and quasars. Despite their enormous power, relativistic jets are transient on cosmic timescales. They flare, fade, and sometimes vanish as the supply of accreting material changes. When the central black hole enters a quieter phase, the jets weaken, leaving behind relic lobes that persist for millions of years before dispersing. These relics, still glowing in radio frequencies, mark the history of activity cycles within galaxies. By mapping them, astronomers reconstruct how black holes have influenced their surroundings over time, transforming gravitational energy into a cosmic archive written in plasma and light. The study of jets unites many branches of physics: gravity, electromagnetism, plasma dynamics, and relativity. It shows that black holes are not endpoints, but engines converting the potential energy of infalling matter and the rotational energy of spacetime itself into motion that reshapes the universe. From the smallest microquasars within our galaxy to the largest radio galaxies spanning millions of light years, the same principles govern their formation and behavior. Each jet is a visible reminder that even near the edge of darkness, the universe remains dynamic, translating collapse into creation through the immutable laws of nature. The exploration now turns still closer to the black hole's boundary, to the radiation that escapes from its immediate surroundings, and the subtle polarization of that light signatures that reveal the structure of magnetic fields and the extreme curvature of spacetime just outside the event horizon. Light that escapes from the regions surrounding a black hole carries the imprint of everything it has encountered: magnetic fields, moving plasma, and the curvature of spacetime itself. Though the black hole emits no light directly, its environment glows with radiation produced by matter before it vanishes beyond the event horizon. This radiation spans the entire electromagnetic spectrum and provides nearly all the information scientists possess about these hidden objects. Each photon that reaches an observer carries subtle distortions in its wavelength direction and polarization, revealing details about the structure of the disk, the power of the magnetic field, and the nature of spacetime near the boundary, where light barely escapes. The study of this radiation transforms darkness into knowledge, using light bent and scattered by gravity to trace the unseen. The spectrum of a black hole's surroundings depends on the temperature and density of its accretion disk. In the outer regions, cooler gas emits visible and ultraviolet light. Closer to the horizon, where temperatures climb to millions of degrees, the radiation shifts into X-rays and gamma rays. This continuous gradient creates a multi-wavelength portrait of activity. By observing across bands, astronomers can reconstruct how energy is distributed from the outer edges to the inner core. Variability in these emissions flickers, pulses or flares arises when magnetic reconnection or turbulence alters the flow of plasma. Each variation provides a glimpse of dynamic processes otherwise hidden behind gravitational walls. The motion of matter near the black hole adds another layer of complexity. As gas orbits at relativistic speeds, light from the approaching side of the disk becomes blue-shifted, while light from the receding side is red-shifted. These shifts blend into broadened spectral lines that mark the influence of gravity on energy. The shape of these lines reveals the velocity of rotation and the depth of the gravitational potential. In extreme cases, the broadening becomes asymmetric, producing characteristic curves that betray the black hole's spin. Measuring such distortions allows astronomers to estimate how fast a black hole rotates, a property that influences everything from accretion efficiency to jet power. Polarization adds another dimension to the study of radiation. Light waves oscillate in specific directions, and as they pass through magnetic fields or scatter off charged particles, their orientation changes. By measuring these changes, scientists map the geometry and strength of magnetic fields near the black hole. Polarimetric observations from instruments like the Event Horizon Telescope have revealed swirling polarization patterns that trace field lines wrapping around the accretion disk. These measurements confirm that strong organized magnetic fields exist even at the threshold of the event horizon, guiding both inflows of matter and outflows of energy. The orientation of the polarized light also helps determine the direction of the black hole's spin and the inclination of the disk, turning subtle patterns of light into a form of cosmic cartography. Radiation from near a black hole does not travel in straight lines. The curvature of spacetime bends its path, creating visual effects that defy ordinary perspective. Light from the far side of the disk can curve around the black hole and reach the observer, allowing both sides of the disk to appear simultaneously. This gravitational lensing creates a bright ring of light, known as the photon ring, a boundary where photons orbit multiple times before escaping. The ring's apparent size and shape depend on the black hole's mass, spin, and viewing angle. The event horizon. Telescope's first images of the black hole in Messier 87 showed precisely this structure, a glowing ring surrounding a dark center, matching the predictions of general relativity to extraordinary accuracy. The photon ring marks the outermost visible manifestation of extreme gravity, but deeper within lies the region where radiation becomes trapped. At the inner edge of the accretion disk, the innermost stable circular orbit defines the limit beyond which matter can no longer maintain stable rotation. Inside this orbit, material plunges rapidly toward the event horizon, releasing its last burst of energy before crossing into darkness. The light from this region is redshifted by gravity stretched to longer wavelengths as it climbs out of the potential well. To distant observers, this emission appears faint and delayed, providing a natural boundary between what can and cannot be seen. The subtle interplay between energy release and gravitational redshift shapes the observed brightness of accretion disk, offering a way to test predictions of relativistic physics with precision. Another feature of black hole radiation is the corona, a region of hot, tenuous plasma hovering above the accretion disk. This corona acts like a cosmic amplifier, scattering low-energy photons from the disk into higher energies through a process called inverse Compton scattering. The result is a hard X-ray component that varies rapidly in brightness, often in correlation with changes in the disk itself. The structure and origin of coronas remain subjects of study, but they appear to be linked to magnetic activity similar to that seen on the Sun, though vastly more powerful. Together, the disk, corona, and jet form an interconnected system where matter and energy circulate through cycles of inflow, heating, and ejection. Time plays an unusual role near black holes. Because gravity slows the passage of time, photons escaping from near the horizon experience dilation relative to those emitted farther away. This means that observers see light from inner regions as delayed or smeared, producing echoes that can be used to map distances within the system. By studying these reverberations, astronomers reconstruct the geometry of the accretion flow. These techniques, sometimes called X-ray reverberation mapping, have revealed that inner disks and coronas shift and fluctuate in response to changes in accretion, behaving like pulsating structures bound by relativistic constraints. Radiation also allows black holes to be weighed with remarkable accuracy. The luminosity of the accretion flow, when combined with measurements of orbital speeds and the extent of gravitational redshift, yields mass estimates consistent across methods. For stellar mass black holes, masses are determined through the motion of companion stars. For supermassive ones, measurements of gas and stellar orbits within galactic cores provide values reaching billions of solar masses. The consistency between dynamical and radiative methods reinforces the universality of gravitational law across more than 10 orders of magnitude in scale. Yet even as radiation reveals so much, it conceals what lies beyond the horizon. No signal can emerge from within that boundary. Light emitted even infinitesimally inside cannot escape. The event horizon thus forms the ultimate edge of observation. Beyond it, the predictions of classical physics end and only theoretical extrapolation remains. This boundary is not a physical surface but a region defined by geometry, a point of no return where paths of light and matter curve inward forever. Observing how light behaves just outside this region tests the limits of general relativity, probing whether the equations hold under the most extreme conditions. Each photon, each spectral line, and each polarization angle forms part of a silent conversation between light and gravity. Radiation from the edges of black holes reveals not destruction, but order, an equilibrium maintained by precise laws operating at unimaginable intensities. The next inward step will move beyond what light can show into the realm where gravity itself becomes the only messenger, the domain of lensing shadow, and the photon ring where the bending of light transforms observation into geometry, and the universe discloses its shape through curvature alone. As light passes near a black hole, its path bends, tracing arcs through the warped geometry of spacetime. This bending, known as gravitational lensing, is one of the clearest demonstrations of general relativity. It reveals how gravity does not act as a force pulling on light, but as the curvature of the space through which light travels. Near ordinary stars, this effect is subtle, producing gentle distortions of distant starlight. Near black holes, it becomes profound. Photons curve so sharply that some orbit multiple times before escaping, creating luminous rings and mirrored images that surround the dark center. To observe a black hole through its lensing is to see spacetime itself acting as a mirror folding the universe around an unseen point. The physics of lensing begins with the geometry of curved space. According to Einstein's equations, mass and energy determine how spacetime bends, and that curvature dictates how objects move. For black holes, the curvature becomes so extreme that light can follow closed paths. The radius at which light can orbit indefinitely is known as the photon sphere. Any photon that approaches closer spirals inward and disappears. Those that pass slightly farther away are deflected, producing the bright circular pattern called the photon ring. The thickness, brightness, and asymmetry of this ring encode the black hole's mass, spin, and orientation. A perfectly spherical, non-rotating black hole would produce a symmetric ring. Rotation distorts it, making one side brighter and narrower due to the relativistic beaming of light from material moving toward the observer. Observations from the Event Horizon Telescope have made these predictions visible. The first image of the black hole in the galaxy Messier 87 displayed a glowing ring surrounding a dark core, its diameter corresponding precisely to that expected for a black hole of 6.5 billion solar masses. Later imaging of Sagittarius A in the Milky Way confirmed the same pattern on a smaller scale. These images, constructed from radio waves collected by telescopes around the world, represent not photographs in the ordinary sense, but reconstructions of light's behavior in curved space-time. They stand as direct evidence that gravity warps the paths of photons exactly as general relativity describes. Beyond direct imaging, gravitational lensing around black holes produces observable effects at greater distances. When a black hole passes in front of a background star or galaxy, it magnifies and distorts the background light, sometimes splitting it into multiple images. This effect, known as microlensing, allows astronomers to detect isolated black holes otherwise invisible. In rare cases, a perfect alignment creates an Einstein ring, a complete circle of light surrounding the lensing object. On cosmic scales, similar lensing effects caused by clusters of galaxies reveal the distribution of dark matter throughout the universe. Around individual black holes, these same principles operate in miniature, demonstrating that gravity's curvature applies at all scales. The photon ring seen in simulations and observations represents more than a visual feature. It is a record of photons that have orbited the black hole several times before escaping. Each successive orbit produces a fainter, more tightly curved ring nested within the previous one. In theory, these higher-order rings contain an infinite sequence of reflections, though in practice only the first few can be detected. They encode an immense amount of information about the geometry of spacetime near the horizon, including the effects of rotation and the warping of time. Future telescopes with higher resolution may resolve these subrings, allowing direct test of how gravity behaves at its strongest. Lensing near black holes also affects the polarization of light. As photons follow curved paths, their polarization vectors rotate, tracing the twisting geometry of spacetime. Measurements of this rotation provide another way to probe the structure of magnetic fields and the validity of relativity. In the images of Messier 87's black hole, the polarization patterns form spirals that match predictions from magnetohydrodynamic simulations, confirming that the light's orientation carries memory of both magnetic structure and gravitational curvature. The most extreme lensing occurs in systems where two black holes interact. When they orbit each other, their combined gravitational fields create complex distortions, producing rapidly changing patterns of brightness. During the final moments before merger light from one black hole can be lensed around the other, creating fleeting echoes and arcs that flash across space. These effects are difficult to observe directly, but appear in detailed simulations illustrating how dynamic and fluid spacetime becomes under such conditions. The gravitational waves produced during these events carry complementary information, revealing the motion of mass rather than light. Together, lensing and waves offer two ways to perceive the same geometry, one through photons, the other through ripples in spacetime itself. On larger scales, gravitational lensing by supermassive black holes can influence their host galaxies' appearance. Jets and gas illuminated by background light can appear distorted or multiplied by the curvature near the core. These subtle effects, though faint, can be detected through precise mapping of light intensity and position. Such measurements allow astronomers to refine estimates of black hole mass with extraordinary precision. In some galaxies, the apparent brightness of distant quasars fluctuates as their light passes near intervening black holes, producing time-delayed variations that trace the distribution of invisible matter along the line of sight. The concept of lensing also extends into theoretical questions about what might lie beyond the observable horizon. Some physicists propose that if exotic forms of matter or quantum effects alter the structure of spacetime near the singularity, they could slightly modify how light bends. Detecting any deviation from predicted patterns would reveal new physics beyond general relativity. So far, every observation agrees with Einstein's equations, but as instruments become more sensitive, even minute differences could point toward a deeper theory of gravity. From a visual standpoint, gravitational lensing transforms perception itself. Near a black hole, light no longer travels in straight lines, and distance loses its ordinary meaning. The front and back of the accretion disk appear simultaneously mirrored by curved trajectories of photons. The region behind the black hole becomes visible around its edges as light from that side bends around to meet the observer. This means that when viewing a black hole, one does not see a single perspective, but a complete distorted panorama of the surrounding universe, compressed into a circular frame. Time, too, becomes entangled in the image. Light emitted at different moments can arrive, simultaneously layering multiple histories into one view. The photon ring thus represents more than a physical boundary. It is the visible edge of causality, the threshold where light skirts the limits of escape. Its persistence across every scale from stellar to supermassive demonstrates the universality of gravitational law. Whether surrounding a few solar mass remnant or a billion solar mass core, the same circular form appears scaled only by mass and distance. To look upon that ring is to see the shape of spacetime itself made visible through light. From here, the path of exploration moves inward once more toward the event horizon proper, the surface beyond which even light cannot return. There, gravity ceases to be a distant influence and becomes the defining structure of existence, altering the flow of time and the fabric of reality at its most fundamental level. The event horizon marks the boundary between what can be seen and what can only be inferred. It is not a surface in any ordinary sense, but a region defined by geometry, where the curvature of spacetime is so steep that all paths lead inward. For an external observer, it represents the limit of visibility, the point beyond which information cannot escape. Light emitted just above the horizon climbs outward with ever-diminishing energy, appearing slower and redder until it fades into darkness. Inside space and time exchange roles, what was once a direction in space becomes an inevitable flow toward the singularity. The horizon thus divides the universe into two domains, one open to observation, the other hidden within the equations of gravity. The structure of this boundary depends on the black hole's properties. For a non-rotating uncharged black hole described by the Schwarzschild solution, the horizon forms a perfect sphere. In the case of a rotating black hole known as a Kerr black hole, the horizon flattens slightly at the poles and expands at the equator, reflecting the influence of spin. Surrounding it lies the ergosphere, a region where space-time itself is dragged around by rotation. Within the ergosphere, nothing can remain stationary relative to distant space. Everything is compelled to rotate with the black hole. However, matter can still escape if it moves in the right direction, and in doing so it can extract energy from the black hole's spin, a process known as the Penrose mechanism. This interplay between gravity and rotation allows black holes not only to consume energy, but also to release it through intricate relativistic effects. Approaching the event horizon from a safe distance would reveal progressively stronger distortions. Stars behind the black hole appear displaced, forming arcs of light encircling the dark center. Time dilates as gravity deepens. To an external observer, an object falling toward the horizon seems to slow endlessly, its light fading and reddening as it approaches. The object never appears to cross the boundary, even though from its own perspective it does so in finite time. This difference arises from the nature of space-time geometry. Near the horizon, the paths of light that carry information outward stretch infinitely. For the falling object, the horizon is unremarkable. No sudden barrier, only a smooth continuation of motion into regions where all directions lead deeper. Inside the event horizon, the equations of general relativity predict that all matter and radiation collapse toward a single point of infinite density known as the singularity. Here the curvature of space-time becomes infinite, and the known laws of physics can no longer describe events. Time and space lose their conventional meaning, replaced by conditions that require a theory of quantum gravity still to be developed. Some models propose that the singularity may not be a point but a region of finite size where quantum effects stabilize the collapse. Others suggest that information might not be destroyed but somehow encoded on the surface of the horizon, an idea central to the holographic principle. These theoretical explorations remain untested, yet they highlight the black hole's role as a bridge between the macroscopic world of gravity and the microscopic world of quantum mechanics. Observationally, the event horizon is defined by what it prevents us from seeing. The dark region in images of black holes corresponds not to the horizon itself, but to the photon sphere and its projection on the sky. The true horizon lies slightly inside, invisible by any direct means. Its presence is inferred from the absence of light, from the way radiation fades rather than ends abruptly. The sharpness of this shadow and the behavior of matter near it match the predictions of relativity so closely that no alternative explanation has yet succeeded in describing them. Every observation of black holes, from the smallest binaries to the largest quasars, confirms that space-time behaves exactly as Einstein's equations dictate, even at the edge of physical law. The event horizon also determines how black holes interact with their surroundings. Any particle crossing it adds to the black hole's mass, while any emitted energy outside reduces it. Over immense spans of time, a faint process known as Hawking radiation slowly drains energy from the black hole. This radiation arises from quantum fluctuations near the horizon, where pairs of virtual particles momentarily appear. Occasionally one falls inward, while the other escapes, carrying away a tiny amount of energy. For stellar and supermassive black holes, the effect is negligible, far weaker than the cosmic background radiation that surrounds them. Yet over timescales exceeding the current age of the universe, it implies that even black holes are not truly eternal. They will eventually evaporate, leaving behind only residual radiation in the distant future. The horizon can also carry information about its own history. The area of the event horizon increases whenever mass or energy enters, and can never decrease through classical means, a property known as the area theorem. This mirrors the second law of thermodynamics, where entropy, a measure of disorder, always rises. The connection between horizon area and entropy suggests that black holes possess temperature and thermodynamic behavior, linking gravity with statistical mechanics. These insights, developed through the work of physicists in the 20th century, revealed that black holes are not purely gravitational objects but thermodynamic systems. The entropy associated with a black hole is proportional to the area of its horizon, while its temperature relates to its surface gravity. These relationships hint at deep unity among physical laws once thought separate. The region just outside the horizon, where matter accelerates and radiation scatters, remains a laboratory for testing theories of relativity and quantum mechanics. Instruments measure time, delays, polarization changes, and energy shifts in photons emitted from this zone, searching for deviations from expected patterns. So far, all results affirm the precision of Einstein's theory, yet each observation pushes the limits of measurement closer to the ultimate frontier. Future missions equipped with higher sensitivity may capture subtler effects, perhaps slight differences in photon timing or deviations in polarization that reveal how gravity behaves when space and time nearly break down. To contemplate the event horizon is to confront the boundary between knowledge and mystery. Everything beyond it lies hidden from the universe, yet its influence governs everything that can be seen. It embodies both the end of observation and the beginning of speculation, the point where mathematics must replace experience. The black hole's horizon is thus not only a physical boundary, but a conceptual one defining what can be known in a universe governed by finite speed and infinite depth. Beyond that, surface space and time converge toward the singularity, and the known world dissolves into geometry itself. Yet even there, theory suggests that patterns persist, that information, energy, and structure continue in forms yet to be understood. The final stage of this inward journey is the meeting of black holes themselves, where horizons merge, space-time trembles, and the universe speaks through waves rather than light. When two black holes approach each other, their merger becomes one of the most energetic and precisely ordered events in the universe. These encounters occur when galaxies collide, when stellar remnants drift together in dense clusters, or when long-evolved binaries finally close their orbits through the gradual loss of energy. For millions of years they spiral toward one another, exchanging angular momentum with their surroundings, and emitting gravitational waves, ripples in space-time predicted by Einstein more than a century ago. These waves carry energy away, shrinking the orbit and accelerating the dance until the two horizons meet. In the final seconds, space-time vibrates with immense power as the pair coalesces into a single, more massive black hole. No explosion of light marks the event, only the silent passage of waves that stretch and compress the fabric of the universe itself. The process unfolds in three distinct stages. The in-spiral begins when the black holes orbit at relatively large separations. Their motion follows the rules of general relativity, but the energy loss from gravitational radiation is small. Over time, the orbit decays and the frequency of emitted waves increases. As the black holes draw closer, their velocities approach a significant fraction of the speed of light, and the strength of the waves grows dramatically. This leads to the merger stage where the horizons touch and fuse. The gravitational waves reach their peak amplitude, forming a characteristic pattern, often compared to a chirp low frequency, at first then rising in pitch and intensity until the instant of union. Afterward comes the ring down, a brief period during which the newly formed black hole settles into equilibrium. The vibrations of spacetime damp away, leaving behind a stable object whose final mass, spin and shape depend on the properties of the original pair. Observations of these events have transformed astrophysics. In 2015, the Laser Interferometer Gravitational Wave Observatory detected the first direct signal from a binary black hole merger, confirming that gravitational waves travel through space exactly as predicted. Since then, dozens of such events have been recorded, each revealing details about masses, spins, and distances of systems previously invisible. The detected signals show that black holes merge across a wide range of scales, from stellar pairs only a few times heavier than the Sun to intermediate systems hundreds of solar masses in size. Future detectors will extend this range further, capturing the deep rumble of supermassive black holes merging in the distant universe. The gravitational waves themselves carry pure information about gravity. Unlike light, which can be absorbed or scattered, these ripples travel through matter unhindered, arriving at detectors with their structure intact. They provide a direct record of motion in spacetime, unaffected by intervening gas or dust. Each wave encodes the story of its source, the mass and spin of the merging black holes, their orientation, and even the angle from which the event is viewed. When multiple detectors on Earth capture the same signal, triangulation allows astronomers to locate the source in the sky. Coordinated observations with electromagnetic telescopes can then search for accompanying signals, though black hole mergers are usually silent in light. When a black hole merges with a neutron star, however, the collision can produce flashes of radiation that bridge both realms of observation. The power released during a merger is immense. For a brief moment, the energy emitted as gravitational waves can exceed that of all the stars in the observable universe combined. Yet this energy is not destructive. It spreads thinly across space-altering distances by less than a fraction of a proton's width, even as it passes through Earth. Sensitive interferometers detect these minuscule distortions by measuring the change in length between mirrors separated by kilometers, translating microscopic motion into cosmic revelation. Each detection confirms that spacetime behaves elastically, responding to massive motion, as water responds to a stone's ripple. The final black hole formed from a merger possesses characteristics that reflect conservation of momentum and energy. Its spin may be rapid, produced by the combination of the original angular momenta. Its mass is slightly less than the sum of its parents because part of the total energy has been radiated away as waves. Numerical simulations reproduce these outcomes with striking accuracy, matching observations to fractions of a percent. These simulations, running on supercomputers, solve Einstein's field equations step by step, evolving curved spacetime through the collision. The agreement between theory and observation stands as one of the greatest validations of modern physics. As gravitational wave astronomy advances, the ability to probe earlier epochs of the universe grows. Supermassive black holes formed in galactic centers also merge when their host galaxies collide. The process unfolds more slowly than in stellar systems, taking millions of years for the orbits to decay. The final merger produces waves with frequencies too low for ground-based detectors, but detectable by future space observatories such as the Laser Interferometer Space Antenna. These signals will reveal the history of galaxy formation mapping, when and how the largest black holes assembled. They may also test whether the gravitational constant has remained fixed over cosmic time, and whether spacetime behaves differently under extreme conditions. The ring-down phase that follows a merger offers a unique test of relativity. As the new black hole stabilizes, it emits waves at discrete frequencies known as quasi-normal modes determined solely by its mass and spin. Measuring these frequencies allows scientists to confirm that the remnant conforms to the Kerr solution of general relativity. Any deviation would signal new physics, perhaps indicating the influence of quantum gravity or exotic forms of matter. So far, every observed ring-down matches predictions, precisely suggesting that nature adheres to the mathematical elegance Einstein described. Beyond individual mergers, the universe contains a continuous background of gravitational waves from countless unresolved events. This cosmic hum fills space with faint vibrations, the cumulative memory of every collision that has occurred over billions of years. By measuring this background, astronomers can trace the population of black holes throughout cosmic history, even those too distant to detect individually. Recent observations of correlated timing variations in networks of pulsars rapidly rotating neutron stars that act as precise cosmic clocks have provided the first hints of this gravitational wave background. The confirmation of this signal would open a new window on the large-scale structure of spacetime, turning the universe itself into an instrument of detection. The merger of black holes is both a conclusion and a beginning. It marks the end of two separate horizons and the creation of a new one, smoother and more massive. The process embodies the continuity of cosmic evolution. Matter collapses, merges and stabilizes under gravity's unbroken guidance. Even as energy radiates away, the total structure of the universe remains conserved, its curvature adjusted but not destroyed. The waves that spread outward carry not only information but harmony, a resonance between mass and space that endures long after the event has passed. At the deepest level, such mergers reveal the unity of all scales of gravity. The same equations describe the orbit of planets and the collision of black holes. The difference lies only in intensity. What we witness in these grand cosmic unions is the purest expression of geometry in motion, the bending of space, the slowing of time, the release of energy through curvature alone. In the silence that follows, the ring-down space-time smooths, and the universe resumes its quiet expansion, carrying within its shape the memory of every merger that has ever occurred.